Hello to everybody. We are glad you are joining the seminar of the IAU Commission, the Local Universe. And today we have the talk by Lorenzo Spina, from Padua Astronomical Observatory, and he will talk about chemical resolving of stars of open clusters. So it is very relevant topic investigating our galaxy. So you are welcome, Lorenzo, to share your screen and start.
Okay, I'll start now. Okay, I think you can see everything. So thank you, first of all, Grazina, for inviting me and for this great opportunity to talk about our latest result on chemical tagging. We have recently published these results in Astronomy and Astrophysics like 2 weeks ago, so it's still in press. And but you can find the paper in the archive. Of course, if you want to know more, go there and check it out, or you can write me and I will be very happy to answer the questions and also receive your comments. So I would like to start with something that is really at the basis of the concept of chemical tagging, and this something is open clusters. Open clusters are a group of stars that form together at the same time from the same material. And we know that most, possibly all stars in our galaxy have formed in stellar associations like open clusters. That's why open clusters are generally considered as the smallest building blocks of the Milky Way. So some open clusters have survived till today, and in fact we know more than 2,000 open clusters spread out throughout the galactic disk. Like in this plot from the paper of Cantat-Godin, we can see the clusters that were known at that time. Now we know even more clusters, but you can easily see how they are spread. Here we have the distance from the galactic midplane and the distance from the galactic center. However, we also know that most of the open clusters that have formed during the history of the galaxy are now dissolved. And we can see this nice simulation among many others, a simulation about the disruption of an open cluster. We start with a very dense group of stars, which will evaporate with time. The cluster is dissolving because it is kicked by the gravitational potential of the galaxy, like the spirals, the central bar and other things, the molecular clouds. And from this movie, we can really understand how this process of cluster disruption is very important for the evolution of the galaxy, because it continuously feeds our Milky Way of new stars that then are free to wander throughout the galaxy, free from their siblings. So most of the stars that we observe today have traveled a long way from the orbits in which they were born. And now it is difficult to figure out where they came from. And that's represent a really big problem for those who, like me, Laia, or Grazina, and many other people want to reconstruct the history of the Milky Way. So the big question that we should ask to ourselves in order to fill this important gap of knowledge is the following: is the information about the origin of stars really lost forever? And here we come to chemical tagging. So we have said that the stars form in clusters, and stars form within the same cluster have formed from the same material, so they should be chemically identical. Thus, under this assumption, one could use the chemical partner of stars to tag two stars that form together, and in this way reconstruct the building blocks of the Milky Way. So we are using chemical abundances to tag stars, and that's why this approach is called the chemical tagging. So imagine an ideal world where there is a method that you can use to reconstruct the smallest building blocks of the Milky Way that are now completely dispersed. So this approach, if it works, could allow an epochal revolution in the study of the galaxy, and could also allow us to find groundbreaking discoveries. Okay, so to which extent chemical tagging is really feasible? The success of chemical tagging relies on two fundamental assumptions. First, stars formed within the same environment must be chemically identical. And second, different environment must be chemically dissimilar. Otherwise, you will not be able to really identify or distinguish different chemical environment, different environments from the chemical point of view. So it has been shown that chemical tagging can work for halo objects, such as stellar streams and globular clusters, because they have a very different chemical composition, but the story may be completely different in the thin disk. In fact, it has been shown that open clusters have a very similar composition, so it's not really trivial to say if chemical tagging can work also for open clusters and in the thin disk. So to which extent the chemical tagging is really feasible in the galaxy, and in particular in the thin disk? That's why we have carried out an innovative experiment that tries to answer this question, and from which we have obtained some unexpected results. At least they were expected to me. So, and I will show you these results later. So this experiment consists in studying if stars form a dense group in the chemical space. For example, here we have a two-dimensional chemical space. We have the elemental abundance 1 and the elemental abundance 2. And people usually study if these stars are clustered or they form overdensities in this space. And also if this group of stars correspond to real open clusters. So in the past, people have used the clustering algorithms such as K-means, dbScan, or HDBScan to detect overdensities in the chemical space, and then divide these stars in groups if they belong to some of these groups. However, we have used a different algorithms that works in a slightly different way. This algorithm is called optics. It does not immediately divide the data into clusters. Instead, it first reorder the data set in a way that two stars with a chemical partner are one next to the other in the new ordering. And also it assigns to each star a quantity that is called the reachability distance. And this reachability distance can be seen as the average density around each star in the chemical space. So, for example, so stars belonging to the same cluster are confined within the same valley or dip, like in this case. For example, here we have the sea, we see the blue stars. These stars here are in the denser part of the cluster, while these stars here are more located in the outskirts. Okay, simply because these stars have a smaller reachability distance. So you can also distinguish between clusters that are more dense from clusters that are less dense. And also you can distinguish subclusters in this way. So that's why we have used the optics, because it's less a black box than K-means or dbScan, for instance, because you can really access what's going on inside of the clustering algorithm. It allows you to extract clusters of different densities, and also it allows you to extract subclusters. Although other algorithms like HDBScan also allow to extract subclusters and clusters of different densities. So yes, so there is something else that I would like to point out. So the performance of these clustering algorithms depends on a set of hyperparameters that have to be tuned. And usually people typically people have tuned these hyperparameters in order to maximize the recovery rate of open clusters that they wish to recover, which is a very obvious approach. But we have decided to use a slightly different approach, which is a blind, we call the blind chemical tagging. So we have never used the open clusters that we want to recover for tuning the hyperparameters. And that's important because this kind of approach is the kind of approach that really simulates a real attempt of chemical tagging. There are many other aspects of novelty in our analysis. I don't want to bore you with many technicalities. If you want to know more, you can check the paper or you can ask me questions at the end. But I would like to summarize a few points. So first, not many people know that these clustering algorithms are not entirely deterministic. And this means that their performances slightly depend on how the stars are ordered in the dataset. And we demonstrate that pre-sorting the dataset based on the chemical abundances ensures a better performance of the clustering algorithms. And so we have done that, of course, but this is demonstrated in the paper as well. Then the standardization. With standardization, you scale the chemical abundances in order to give them an equal weight. So in equal weight when they will be analyzed to the clustering algorithms. This is typically a must in every clustering analysis in data science in general, but it's not always carried out in astronomy, unfortunately. Then the Manhattan metric. This I think is the most interesting point because we have demonstrated that Manhattan metric is more stable against noise than the Euclidean metric. And I think that we have been the first to use this metric for chemical tagging problems. And finally, dimensionality reduction. So spectroscopic surveys typically are able to analyze several elements. In our case, we had 19 elements for which we had abundances. And people usually think that the more elements, the better, but the reality is actually different because it is a consolidated fact in data science that clustering algorithms are not very efficient in high dimensional space. That's why we reduce the dimensions of our hyperspace using the principal component analysis and then the linear discriminant analysis. You can find more details in the paper, or you can ask me later if you want to know more about that. So first thing first, we carried out a preliminary test to see if everything works well, given the strategies that I showed you before. And for this test, we analyzed a data set that was composed by 190 stars divided in 13 open clusters. Only for this test, we carried out a non-blind analysis. So we tuned the hyperparameter based on the recovery rate in order to maximize the recovery rate of these clusters. And this is the reachability plot that was produced by our analysis. Each point here is a star. It is colored based on its actual membership to the clusters, and the vertical bands represent the open clusters that we have recovered at the 50% homogeneity and 50% of completeness. The homogeneity is the number of open clusters within each group divided by the number of components of the group. For instance, the yellow group here, you can see, is basically almost exclusively composed by yellow points. So it is very homogeneous. More homogeneous, for example, than the brown group here, which has some blue point, one orange point, etc. Okay, instead the completeness is defined as the fraction of open cluster members within the group. For instance, the pink group here includes all the pink points in this plot, so it is a 100% complete. Instead, for example, this green group here is missing some stars, some green stars, so it's less complete than the pink group. Okay, so based on this criteria, we have been able to recover 9 open clusters, which is a very large number compared to other studies based on non-blind analysis, like the study from Malaya that was composed by 99 stars divided in 14 open clusters, and they have been able to recover 4 open clusters. But I need to stress that it's difficult to compare 2 data sets, because Laia, tell me if I'm wrong, but your data set was composed mostly by local open clusters, and of course the local open clusters are more similar than the open clusters that we have here, that range from 6 kiloparsec to 13 kiloparsec. So of course we are in a better position to distinguish clusters. However, we were very satisfied with this number compared to what it has been achieved in the past. So after the preliminary test, we can proceed to the real blind analysis. Our data set was composed by 758 stars, divided in 3 subsamples. So the first subsample was the subsample that I showed you before, is the tuning sample composed by 190 stars divided in 13 open clusters. And we used these stars to tune the algorithm. And once the algorithm was tuned, then we have removed these stars. And then we have the target sample, so 112 stars divided in 23 open clusters. And these are actually the open clusters that we wish to recover from our analysis with the chemical abundances. Plus, we had 456 stars from the field, so stars that up to our knowledge were not associated to any cluster. So after, as I said before, after we tuned the hyperparameters, we discarded the tuning sample and we just analyzed these 2 subsamples here, and this is the reachability plot that we obtained. As you can see, there are some dips, some valleys corresponding to high density regions. These are very evident. There are others that are less evident. We identified the 77 candidate clusters, so 77 high density group in the chemical space. But we selected for further studies only 14 groups formed by stars with very similar kinematics. And among these groups, we found that we found that 3 of these 14 groups correspond to real open clusters at the homogeneity and the completeness of 50%. Okay, so yes, so these are the groups, the 3 groups corresponding to the 3 clusters that we have been able to recover. For each line, we have a group, and for each line, we have 3 panels. Here, for example, we have the radial action as a function of the angular momentum of these stars. So the colored points are the stars in the group, while the blue points are all the other stars that we have analyzed. Here we have the azimuthal action as a function of the angular momentum, and here we have the distance from the galactic plane as a function of the galactocentric distance. So, for example, this first group is not very homogeneous because it contains members of 3 different clusters plus a couple of stars from the field, but it includes 4 stars out of 5 members from this cluster here, NGC 3960. So that's why we say that we have been able to recover this cluster at the homogeneity of 50% and completeness of 80%. Okay, then we also have this other group, which is entirely composed by stars of the same cluster. So this cluster was recovered with homogeneous of 100% and completeness of 75%. Very happy about that. And then we have this last group that was composed by 4 stars of NGC 2324 plus 1 star from the field. But there are other things that we have found. For instance, we have found a couple of stars that have a nearly identical abundances. So these 2 stars fall within the same group. So they have the nearly identical chemical abundances, but also nearly identical kinematics and nearly identical spatial location. So unfortunately, I cannot tell you more about these stars, not because I'm nasty, because I do not know much about these stars. We should observe these stars more in details. But this is interesting. It's an unknown group. I was not expecting something like this. Then we also found 2 stars from the field that have a similar spatial location and similar kinematics than the 2 stars of Melot 71. That's why we think these stars are possibly escapers, so stars that are leaving the cluster and that we have been able to recover them through chemical abundances. And this is another example of a potential escaper, this star that has a similar chemical composition of the stars of this cluster and also similar spatial location and similar kinematics. We also checked the CN ratio of the candidate escapers, and for these cases, the CN ratio was of these escapers, of these candidate escapers, was similar to the CN ratio of the cluster member. And keep in mind that the CN abundance ratio is a proxy of stellar age for this type of stars. So that might indicate that not only the spatial location, not only the kinematics, not only the chemical abundance, but also the age of the star is similar, which is another hint of the fact that these stars could be true escapers. That's really interesting. That's something that I was not completely expecting from our analysis when we started the analysis. So some conclusions, and then we can open discussion. I would like to know your opinion about this final slide, because actually this is still an open question in my opinion. Unfortunately, we cannot provide a definitive answer to this question. However, I think it's very promising the fact that we have been able to recover some open clusters and also some escapers purely from the chemical analysis. And also we have shown that we should carefully think about the best strategy of a data analysis, because different data sets are different. So a strategy of data analysis that was good for my data set probably will not be good for another data set. So this is something that everybody should keep in mind before attempting this kind of analysis. What's the future of chemical tagging? I don't know. I cannot tell you if it will be feasible or not, at least in the thin disk, but I think that we can already do some important consideration. So I think that the future of chemical tagging relies on 2 important aspects, the data and the clustering algorithms. So we found that the clustering algorithms are extremely sensitive to noisy data. So it's very important to have a precise abundance determination. This is something that is really key. And we have used for our analysis high resolution spectra, UV spectra from the Gaia-ESO survey. So the resolution was around 40,000. So thinking about this, I realized that the future spectroscopic surveys that are planned for this decade will observe at a lower resolution, and this may be a problem, or maybe not. I guess we will see. Of course, we should keep in mind that noise is something that really can kill the clustering analysis. So if we want to attempt chemical tagging in the future, we should provide better data. And then better algorithms. This is something bright in the future because clustering algorithms are extremely important. They are at the center of several business problems. So there are many efforts and investments and a huge support from states and industries to develop better algorithms. Imagine that, I don't know, I use Netflix and my Netflix already knows in advance the movies that I want to watch. And that's a clustering algorithm that predicts what I like and what I don't like based on all the users of Netflix. So there is a huge of money that is invested in this. And so it's very likely that in a few years' time, we are going to have much better algorithms at our disposal, and astronomy will certainly benefit of this huge effort. But it's also true that we need more experts on machine learning in this field because there is a lot to do and a lot to explore. So I will finish here. I'm curious to see your opinion because it's still an open question, or your comments about your what I show you now. Thank you very much.
Thank you very much, Lorenzo. Indeed, this is very interesting question, and those stars escapees, especially it is important to find and in open clusters and in globular clusters, and also we have streams now coming in large numbers. So this is a very important field of research. So now Laia has the question.
Yeah. Hello, Lorenzo. Thank you for the talk. It was very interesting. I have a lot of questions, in fact, but I will try to.
Yeah, I think we can discuss a lot about this.
Yeah. So first, I was curious because for the clusters that you consider well recovered, the ones that you show, maybe you say it in the paper and I missed it, but do they have, for example, if you look at the alpha or iron abundance, are they really special? Or because, for instance, in my experiment that you mentioned, the cluster that was persistently recovered was an alpha enhanced open cluster, like a clearly distinct cluster. And then others were recovered depending on the hyperparameters and how I tuned them, no? But the cluster that was really recovered was this one. And you showed 3 clusters out of how many? 20 or something like this?
Yes.
Do they have something special?
I don't know. I haven't checked that. But I think that the big difference between our studies is that but tell me if I'm wrong, that most of your clusters were more or less local, and then you have a few clusters that we know that they are different, or that they were less local. So that's why probably you find that. I haven't checked that. So that's something that I should better check and see if they are really different from something like, for example, I don't know, I don't remember exactly the age. I don't remember if they are, I don't think they are particularly young. So as you know, young clusters have high S-process elements. So that could also be another factor of importance to discriminate clusters, but I don't have an answer ready for you about this. I will check that. It's a really good point.
Yeah, because if they have some distinctive signature, I mean, you at least can identify why you persistently recover.
And also, Laia, keep in mind that we have projected this high-dimensional space that was 19 dimension into a 5-dimensional space, and this 5-dimensional space it does not correspond to a particular element or 5 particular elements. It's just a projection. So it's it's not trivial at the moment to me to say if one element in particular, like barium, for example, or alpha elements, are more discriminant for these clusters. But this is something that we should look more in detail, of course.
Of course, it would be more to understand like the physical reason why you are recovering them, no? More
yes, and you touched a very important point, because doing the dimensionality reduction makes harder to interpret your analysis. So it's easier to recover a cluster, but then it's less easy to say which are the most important elements for the clustering analysis. So that's another point that I should have added to the discussion.
Okay, we can see.
So,
and then I will ask. Can I ask a second question, and then I will let Friedrich ask his?
Yes, I thought, or you ask at once, or we could make a rotation.
Well, as you wish.
Laia, we can. I'm curious too. So I'm curious to know what you have to say. So write me. Maybe we can discuss.
No, ask Laia, because
it's very short. It's concerning the escapee stars that you mentioned. That was in the previous slide, because of course it's difficult to see, given that you have some contamination in the group and in the groups and the recovered groups, and you expect it, no, to see to interpret if really those stars that belong to the same group in the blind chemical tagging are really stars from the cluster that were disgregated, no. If you look at the kinematics, well, maybe, but it's I don't know. I'm not sure if it's a guarantee of this, because of course when the star escapes from the cluster, the kinematics of the star, I mean, it does not necessarily need to be related to the cluster anymore.
Yes.
So I don't know. When I was thinking about this, it was really difficult for me to try to understand if those stars that will for sure be found and associated to some clusters, how can you really be sure? I see it very, very difficult.
Yeah,
because they can be there by chance in the group.
That's why there are question marks here. Mm-hmm. But I agree. I think age is the key. Age. Mm-hmm. So of course, if you say that the age is the same of the cluster, then I would be at least more confident to remove the question mark that is still here. Mm-hmm. But it's still an interesting question mark. But I see your point, and I would say that you are right.
Mm-hmm. But the determination of age so far has quite large uncertainties.
Yes, so we have used the CN ratio, which is a proxy with not very accurate, not very precise of the age, and this proxy was consistent with the CN of the cluster, but having more, determining ages of giant stars is not something simple, but I think we are providing more questions for the future astronomers or for ourselves. I think so. Follow-up observations would be nice.
Okay, so now Friedrich is waiting.
Cannot hear.
Are you unmuted, Friedrich? We do not hear you. So probably so far Friedrich will fix. We do not hear.
Maybe write in the chat.
So I would like to ask the question. So you used quite many chemical elements, 19, and you say that it is difficult to select which could be more useful for this chemical tagging and which are less. So talking about open clusters, probably it is important if you, for example, use carbon, nitrogen, so they could be altered at different evolutionary stages. So maybe they could serve only as some additional checks afterwards, not in the chemical tagging initial.
Absolutely. And if yes, carbon and nitrogen, and I know that you, Grazina, have contributed to to derive these elements. So they are very important, not for the chemical tagging itself, but for checking later if the stars have similar age. So that's really important. That's something that can help us to verify in the future if we are doing well or not.
Okay, so those elements were not among those 19 which you used?
No. Sorry. Yes, I forgot to ask to answer the main question. No, they were not among the 19. We have kept them out because we wanted to check them, to use them to check these escapers afterwards.
Okay, good. So now, Friedrich, please unmute.
Let's try.
Oh, good.
Is it working now?
Yes.
Okay.
Yes.
Ciao, Lorenzo. I thank you very much for the talk. It was very interesting. I like your different viewing angle on the subject also, because after when we did this paper with Laia, we we were very disappointed. That we were recovering so little clusters actually. And then we had these two experiments. One was with Ocaso data, and the other was with Apogee, where we have basically lower quality data in the sense of the spectral resolution is a bit lower, 20,000, and there were many more field stars in that sample than open cluster stars. And there, the situation was even worse with recovering.
With Apogee, you mean?
In your sample, you have a quite high fraction of actual cluster stars, right? And
yes.
And then you recover only 3 out of the 23 to a certain degree. So, I mean, it's a positive thing. Yeah, at least at least you recover 3. But what about the other 20? They are lost somehow, no?
Yes, that's why I will not be I will not be completely optimistic about the success of chemical tagging in the thin disk. I think we are doing baby steps though, and we are. So this was the first time, at least in my knowledge, of a blind chemical analysis. Clustering analysis. So we have not used the clusters to tune the hyperparameter, and that I think, but let me know if I'm wrong, has not been done in the past, no? And so 3, it's a number. It's better than nothing, and it's it's something at least. And of course, we have to improve the number of stars. We have to increase the data set, and also we have to improve the clustering algorithms. And also we have.
Do you really think the clustering algorithms are the main thing here? Because as you said, the resolution in the next years is not going to go up, right? For the main surveys, it's actually going a bit down. So
no, I think that the main problem is noise. If you look at the current research in clustering algorithms, there is the current research, they are trying to develop new clustering algorithms that are more stable against noise, and also clustering algorithms that can deal with the missing data. For example, it's very common that you have stars with abundances for many elements, but not many. So how do you deal with that? You have to discard the star. And that's not most of the time something that is good for the analysis. So there are these 2 points that are the main points. But I agree that the main killer for this kind of analysis is the noisy data. So we have to work with that. We have used Gaia-ESO data, which have a high resolution. So spectra have a high resolution, but that does not necessarily imply that these abundances are better than the abundances that will be provided by Foremost, because Foremost will analyze the spectra in a different way, or you can also try to analyze. So, for example, something that I would like to try in the future is to do these abundances, but differentially, since these stars are the same type of stars. So you could try to analyze them differentially, so provide the differential abundances, which probably are more precise.
Okay, this is basically then similar to the experiment of Laia, because she has used differential abundances with very high quality, very, very high resolution. And even in the idealized case that you don't have field stars in your sample, only cluster stars, then it doesn't completely work. Yeah.
And how many elements you used, Friedrich?
Maybe Laia, can you can you answer?
Yeah, I don't remember, like more than 10 or something like that. More than 10 in any case. Yeah, different synthetic channels.
To my understanding, in this case, it is very important maybe to use fewer elements, but which have more lines in the spectra, and for which we receive higher accuracy of element determination, because some elements which have very few and weak lines, they simply can destroy our method, and it is better to use.
So I think it's important to like be smart in choosing the elements according to the uncertainties that the abundances that you derive have in those elements, and according also to the completeness of the data, as you were saying, Lorenzo. But I have another thing here, because it's true that, I mean, if you don't get good results, I mean, or you would like to aim to better performance of the clustering algorithm, one would maybe think that it's better to try to get better abundances, no? Try to get better uncertainties, and so the clusters will be more shaped, like more clustered in the end. But so here I see one problem, and is that there is a limit in here where you start to see things happening in the abundances of the stars because of stellar evolution, because of planet engulfment, you know this much better than me, Lorenzo, or because of particularities, not well mixed interstellar medium, whatever, that will place a limit in the uncertainties of the abundances that you can get.
Not very, maybe you're right, but I don't think very much for giant. For example, planet engulfment will not change the composition of giant, and also atomic diffusion, mixing processes only for some elements which are known very well. And so that's why I think we should also focus on some kind of stars. I would not do chemical tagging for dwarfs. I would remove all the dwarfs. I would use only giants, and maybe not all of them. So there are some, so in principle, you are right. That's why we should carefully also select the data set, in my view. And also we should, so for example, the metric is something that we found being important because it deals better with noise. So this is something that I didn't know, honestly. I have learned that studying for the paper, And that's something interesting I was not expecting at all. So I think there are baby steps that we are doing. And also, so your paper has been very important because, so it's, I think, I don't know if it was the first time that HDB scan was used for a chemical tagging, maybe not, but it, but for sure it was a study of very high quality data. And so it's, so I think every work that has been done in the past is providing some new element to think about, and we will see in the future. I agree with Frederick that so there are some, so in the future probably we are not going to have much very good data. So that's a big limitation, I think. But that also means that we have to think about a high resolution large spectroscopic survey. I don't know, I'm just shooting and just proposing things here. So we have to think about these things. I'm not saying that chemical tagging will be completely feasible. I'm just saying that we still have to think about it more carefully and see which are the limitations and what we can really improve, what we cannot improve. So
I would like you, Lorenzo, and everybody not to be so pessimistic. Actually, with a lower resolution, but with high signal to noise ratio, this task could be solved, to my understanding. And we will see that the large work is waiting and the interesting work. So I thank you very much, Lorenzo, for your presentation. Actually, after some time, we will have another talk about open clusters and membership. So you are welcome to our seminars and to look to the YouTube channel who was not able to participate, and we are waiting for your submissions for proposals of other interesting presentations. So today we thank Lorenzo and see you